Hi, thanks, Loga. And I'd like to begin by thanking the organizers for giving me this opportunity to talk about some of my work. And I was told that this is a sort of an introductory pedagogical lecture for all the students. So I'm assuming that that's the case. So, and I've tried to put in sort of different things about the sign problem, just to remind you that last March, actually March 2017, we had a conference on the sign problem, and there were lots of experts in the audience, and we all couldn't agree on what the definition of the sign problem was. So, so this could be a pretty controversial topic if some of you are in that group. But still, I want to give you my perspective on what a sign problem is. I've been working in this area for some time. And I feel that some of the experts have, there are two camps. Some people feel that this is a problem that cannot be solved, so we should just move on and do what we can. And there is another set of us who believe that based on what we have learned over the last decade or so, there's definitely room for new ideas and creativity. And that's what I'd like to do here in terms of young people trying to be excited about this field. But I must warn you that it's a high risk, high reward kind of area. So you jump into the water with that thing. So the outline of the talk is the following. I'll introduce the subject, as I told you, from my perspective. And then I will give you some simple examples, which was very helpful, at least as I was learning about the field, to learn what the origin of the sign problem is. And then maybe you will learn about some of the misconceptions that's around what these sign problems are. And then I will give you, in my opinion, a non-trivial example of a sign problem in quantum field theory. It's just a well-known lattice field theory. It's a very simple lattice field theory. And you will, from the traditional point of view, you will assume that there is a sign problem here, and it'll be as difficult as the most difficult sign problems that you're familiar with. But this is solvable, so I'll show you how you can solve it. And that then teaches you how this notion that sign problems are extremely difficult to solve is just perhaps something that has been carried over as a folklore, so we should really not give up and at least try. And then I will give you another perspective on the sign problem, in the sense that even though you may know how to solve a sign problem, maybe there is another solution, which is a better solution in some sense. So I'll give you a perspective on that. And then maybe this is perhaps more related to this community, in the sense that I will show you that we were able to solve a signal to noise problem, which is sort of like a sign problem. I will explain that. And then we were able to measure some conformal dimensions at large charge, which was very exciting. So this sort of goes back to the connection to the talk that was just before me. So we will talk about that. This is just an introduction to what I will talk about later in my research seminar. So I'll just mention it briefly, that there are Hamiltonian approaches to field theories which are becoming very exciting, at least to me, and I will try to convince you of that. And then I'll present some conclusions. Now this may go beyond. It started as a sort of a 45-minute talk, and then maybe it's more than what the time is allocated to me, but we can stop at any time, and we will come back to any of these other things if I'm not able to cover it. So let me begin with an introduction. So in quantum many-body physics, usually we are interested in measuring some observable. And I'd like to write the observable as a ratio of two what I call partition functions. Because typically, each of these partition functions is a sum over some configuration space, which is exponentially large, that just comes from the large Hilbert space of our problem. And then you have some weights, which you have to sum over. And then the observable is actually a ratio, in the sense that almost all of that big exponential thing just is not important. It's just sort of giving you some background of what the observable is trying to do. So the numerator is some deformation of that thing. But then if you think about it, it's like a expectation value in statistical mechanics, which can be pretty non-trivial, right? Of course, you might ask what type of observables. If you think about observables in real time, typically this weight is completely complex. It's actually a phase, so every configuration is sort of equally probable in that sense that you have to sum over everything, so that becomes extremely hard. Imaginary time problems are much more easier to handle in that sense that maybe there is some hierarchy of the configurations that are important and some are not, right? In either case, I think if you really formulate the problem at the end, this S of C can turn out to be complex in itself. That depends, of course, on the problem that you're trying to do. In most the simplest problems, SC will turn out to be real. So the real-time problems are still, in the simplest case, difficult to solve, whereas the imaginary time problems are easier to solve. So that's why we are able to make some progress in equilibrium physics, essentially. So non-equilibrium physics is much more complicated in that sense. But still, so I will mostly focus on imaginary time problems where the thing seems to be easy, but then still there are lots of interesting questions that turn out to be very difficult to solve. So we all agree, I guess, that that's the reason why things are extremely difficult to solve in quantum many-body problem. So let me tell you what my perspective on what the sign problem is. So we are trying to compute, as I told you, an observable, which is sort of written as a ratio of two sort of quantities of this type. And then you want to find the result, of course. And we, of course, in physics, often cannot really solve the problem exactly. If we can solve the problem exactly, then we are done. That's great. But suppose we want to solve the problem with some error, right? So that's sort of the error in the problem. And then you ask, what is the time it takes to compute this object? And if the time scales polynomially in the system size and 1 over error, then the statement is that there is no sign problem, right? Now, if that doesn't happen, if there are exponential, if the time takes an exponentially long time, either because as the system becomes large, it's difficult to do, or because if you want to make the error smaller and smaller, there is an exponential cost. In either case, I would claim that there is a sign problem. Now, practically, of course, if you say there is no sign problem, still we are in not good shape if this omega and omega prime turn out to be big numbers. So if you really want to make progress, you would like to make these omega and omega prime small. So that then goes back to the question of whether you have a more efficient way of calculating this issue or not. So the challenge, of course, is can we solve these sign problems? In the sense, can we get a polynomial time to compute our quantities? Of course, the best methods would be analytic. If you could really do a perturbation analysis and resum everything. We already learned beautiful things that we could do if we could understand that. So maybe that's the way to go. I'm going to concentrate more on numerical methods, especially Monte Carlo methods, where this object looks very much like an expectation value in a statistical mechanics problem. So why not sort of just choose this to be the Boltzmann weight? And then if this is actually greater than or equal to 0 and computable in polynomial time, this is a very important thing, then we can perhaps use Monte Carlo sampling to obtain this object. That's exactly the way we've been doing many of the Monte Carlo calculations. So in that case, the Monte Carlo result is given by sum over sort of n terms, where n, so these objects are distributed according to this weight W of C. And then the errors are polynomial, and so we are done. However, it's important to note that although WC may be positive, if you really go about trying to solve this O and find an algorithm, really try to obtain this, the errors may not actually go like this, right? In that case, the algorithm is inefficient. So let's think about what are the sources of inefficiencies. Now, I'm assuming that WC is positive. And what happens, in this case, one is an issue with autocorrelation times. So this formula is only valid if you assume that all the CIs that are generated are decorrelated, they're statistically independent. But that can sometimes take a long time. The Monte Carlo takes a long time. And in this case, for example, in theories like quantum chromodynamics, where there is a topology involved, sometimes the algorithms take an exponentially long time to tunnel from one to the other. So you need to sort of worry about that. So that's one issue. Another issue can be there is a very bad signal to noise ratio. So for example, if your observable that you're computing is an exponential decay in some there is a mass and a time scale involved, then and your observables themselves for each thing are phases or things that are of order 1, then you can see that you need a lot of statistics before you can actually get this answer. This is sort of a signal to noise ratio. And then the sign problem in some sense is hidden in this observable, and so it's coming back. And so such problems, you need to think cleverly as to how to solve this issue. And there are interesting quantities that have been calculated which exponentially decay but still can be calculated in polynomial time, and there is a nice method of Lucier and Weiss on that. So that's all great if WC was greater than or equal to 0, but more common is that WC will be negative or complex, and this is just a fact that we have to live with. So the number of problems we can actually solve where WC is greater than or equal to 0 is in fact, to be honest, is measure 0 almost, right? So there are lots of problems which are very interesting, especially once you think about condensed matter physics, where WC is indeed negative. Then the Monte Carlo method is not even applicable. We don't even know what is the right way to sample with. In real time, it's sort of obvious, right? So I'm not even going to worry about that. So let's talk about imaginary time. And in the imaginary time case, we think WC seems real because that's the way we really usually think about the problem. On the other hand, this S of C can be complex, and there are lots of reasons why this happens, right? It's very, very normal. It's not something subtle, and it's extremely simple. And there are also lots of simple quantum mechanical examples where this particular thing happens. So this leads to the computational complexity of quantum many-body systems, is that you have to most of the time deal with W of C, which is complex. Okay, so what can we do? So consider, again, our observable. And the nice feature is that this representation that I gave you is not unique. You can actually write it in many, many ways. And usually what we have done is, it's a historical coincidence that we are taught to do quantum field theories and quantum mechanics in a particular variable. This is maybe because Feynman was famous, maybe because this is what your professors taught you to do, but there is a lot more room, and often we don't think of all these other variables to think about, and so there is a lot of creativity in writing down this observable. So the idea is to find a representation where this WC is greater than or equal to 0 and computable in polynomial time. It's easily said than done, but if you can find this, I'm going to say that the technical first step in your solution is solved, and that's what I call the solution to a sign problem, right? So there are lots of interesting problems out there where we don't even know how to do this particular first step as to, can we write O in this particular way where WC is all positive, right? And if you can do that, let's all agree that we will call it as the solution to a sign problem. Yes? As I told you, again, this is the first step, right? And then you can see there is also the next step, right? So now you need to find an efficient Monte Carlo to be able to compute the observable. So if you do a reweighting, you could do a reweighting and declare victory that you have solved the sign problem, but this will come back to haunt you. So you're completely right that both the steps are important, and so if you do something very naive at the first step and say, oh yeah, I've solved the sign problem because I'm going to do a reweighting, the next step will come back to haunt you, right? So it's going to become exponentially hard. Yes?
Yeah, I still don't understand what you meant precisely when you said the sign problem has something to do with whether or not you can compute W in polynomial time.
Not W.
Not W, sorry. But
sorry, so...
you move back.
Okay, let's see. So, I want to be able to compute this observable in polynomial time, not just W, right?
Okay.
So, you want to actually find the right W, as was pointed out. You just don't want to choose a wrong W. If you choose a wrong W, then this O of C will have so much fluctuations that it'll be very hard to compute O in polynomial time. It'll be exponentially hard to compute this object.
Okay, and my second question is, does everyone agree that this is a good definition for the sign problem? And what are the other definitions? I don't have a background in this, so that's why.
Yeah, so let's talk about this later on. I think we are going to go, and this was a 15-minute to 20-minute conversation at the conference. It took 45 minutes, and we didn't agree.
That's all right. So thanks.
I would be happy to talk about it later on. So I think it's a good question. So these are exactly the issues, right? So the definition that I have is you can actually choose any WC that you want and say it's all positive. So let me declare that the solution to the sign problem is done. But then the numerator or this observable will still be exponentially hard to compute. So So I'm assuming that there is something nice about this WC where the remaining so the WC is distributed in the right way such that the remaining fluctuations that you would like to calculate this OC is reasonable. It's not going to get into an exponential problem. So remember, the final thing is to be able to compute this observable. No, these are all sort of just the steps towards that problem. So we want the full solution actually requires two steps. One is to find this, and the next is to find an efficient algorithm that can compute this observable in polynomial time with a given error. So so that is sort of the introduction as to what I think the sign problem is, and let me give you some very simple examples of where the sign problem comes by. And I have a few examples that I've considered. They're all simple, but then explain to you sort of why there are sign problems, right? So let's first think about. So one of the things that I'd like the students to understand is that there is a sign problem at finite density QCD. This is something that I'm sure many of you learn, and this sign problem haunts many other areas of physics also. It's not just at finite density QCD. But what is the origin of this? Is it sort of surprising that at mu equals 0, we didn't have any sign problem? At finite mu, suddenly there is a sign problem? This is not actually very surprising. The reason is because let's just think about quantum mechanics. And let's say there is a charge, there's a quantum mechanical, there's a charge, and then the conjugate variable is theta, right? Instead of x and p, I'm thinking about a charge and an angle. And I'm going to think about a compact variable, so I write instead of theta, I write e to the I theta and e to the minus I theta. They are much more well behaved. So then I construct my usual algebra, and that's the space, the vector space in which the quantum mechanics lives. There are two basis states. We all learn this in quantum mechanics. One is the basis of charges, so Q acting on the state Q just as a Q, and that Q can take any value, right? Any integer value, and it's a nice normalizable state. Whereas I can also take a state in my angle, which is a state of phase of phi acting on this gives you e to the I theta times theta. And now that's a continuous variable, and that's a non-normalizable state, but we know how to deal with such states in quantum mechanics. And now let's say we want to write down a simple lattice theory, just to give you a sense. I have some temperature beta, which is, I write it as LT times epsilon in small units, and I write down the partition function as usual, right? And then, so this is a pictorial way of thinking about it. There is an epsilon is the lattice spacing in time. These are the lattice sides. There are LT steps. The continuum limit, of course, is epsilon goes to 0, LT tends to infinity, such that LT times epsilon is fixed. Now I need to give you what is H. I'm going to choose an H that describes an energy for a charge to be some constant times Q squared. This is the usual, like let's say a particle with an angular momentum, right? So angular momentum is basically Q. I'm sort of replacing that with the charge Q. So then, oops. Did I miss a? I think I missed it. Yeah, oh, sorry about that. I think I missed a whole slide here. Okay. So the H that I'm going to write down is, remember, is just diagonal in the charge space and goes like lambda times q squared. But I'm going to write a slightly more sophisticated expression for e to the minus epsilon h, and that slide that missed was this. And that h is exactly this object here. E to the minus epsilon h is written in this complicated way through this modified Bessel function, and see why I'm doing that. Because if I take epsilon to 0 of this is a very nice limit, and it gives you just lambda times q squared. You can go and check with the asymptotic expansion of the Bessel function. This is exactly, will give you h goes like lambda times q squared. If I do that, so basically I have h which is diagonal in the charge space, but now I'm writing the partition function in the theta space, right? And if I do this, and if I calculate the theta, I get this object. And so this small time evolution is exactly some constant times exponential of a cosine of the neighboring theta and theta I plus 1 and minus theta. In fact, you can say that this is what my ultimate goal was, and so that's why I took this particular definition of e to the minus epsilon q. Because I wanted to get a nice lattice definition of the Hamiltonian, if you want. So of a transfer matrix e to the minus epsilon h, and that's what I'm using. So what I find is that if I write this and if I substitute this, there is no sign problem. This whole thing is positive, everything is fine, and I have a charge which has energy q squared, and basically I get a path integral which has no sign. This is like the Feynman path integral of a particle with an angular momentum. There is no sign problem. Everything is great. So in the lattice version of this model, I have all these phases, and that's the action, and that's sort of the 1D XY model, if you wish. Now if I go to the grand canonical ensemble, now I say, actually I don't want charges, but I want some charges to be more favored than the other. So in a sense, I add my chemical potential, right, in the usual way, and I now look at the partition function. Now in the charge basis, since h is diagonal in q, this is also a function of q. You see, everything is just a function of q, so there is no sign problem. So we all know that for the partition function, there won't be any sign problem if you go to the diagonal basis of the Hamiltonian, and you also diagonalize the q, because Hamiltonian and q commute with each other, there won't be any sign problem. It's everything sum of positive terms. On the other hand, if I go to the phase basis and I try to do the same thing, now you will see it's very easy to check that this particular thing, if I put in the previous formula, I'll have to put an I in front of it, and so I get this object. And so the action becomes complex in the presence of a chemical potential. So it's just that if you just take the simple quantum mechanical example, we already see that the problem is to work with this theta basis and not the charge basis, right? So if we could write quantum field theories in the basis in which the charge is quantized, this is what is called the world line basis, then there won't be any sign problem, at least because of the chemical potential. So that's one example to take home, and we will come back to this later on. Of course, in realistic problems, it's not just the charge. If the charges are bosons, actually this world line representation actually solves the sign problem completely. This is, of course, known to the condensed matter community for a long time, but it was quite surprising to the lattice field theory community. Interestingly, when this was explained, lots and lots of papers have appeared in this, and people, this whole world line approach has become a big industry, I would say, in the lattice field theory community. But to be honest, this is nothing new. You can find lots of papers of the same type in condensed matter community with Hamiltonian approaches. Okay, so if you think about, now let's think about a second example where we think about two identical particles moving on a periodic lattice, just a one-dimensional lattice, right, a circle. So now I'm going to think about a Hamiltonian approach to this. So just write down a simple free Hamiltonian, like C dagger C. But however, there are going to be two problems I'm going to be thinking about. One will be bosons and another will be fermions, right? These two are two different commutation relations for these creation and annihilation operators. So if there are bosons, of course, you can have many, many bosons on a single side, but I'm going to avoid that by actually making them hardcore. So in a sense, there is an interaction term for the bosonic piece, which I'm sort of hiding. I'm just putting it as a constraint here and saying that there is a hardcore boson there. So the Hamiltonian is as simple as this, except for the hardcore condition of the boson, right? For fermions, I don't have to do it because the Pauli principle, the two fermions cannot come on top of each other, right? So there are two problems here. One is a bosonic problem, one is a fermionic problem, and it's exactly the same Hamiltonian for both, right? In this case, you can actually show that the ground state in this two boson problem is unique, right? Whereas for fermions, you can easily do a simple calculation. In fact, it's a periodic box. The lowest momentum mode is 0. There, the fermion has a 0 energy. And then the next fermion goes to the higher mode, which can have momentum going like this or like that. So there are two different ways in which the fermion can travel. So the fermions are doubly degenerate. They are a doubly degenerate ground state, whereas the boson has a unique ground state. So what is the why is that the case? So if you actually write down the Feynman path integral for this two-body problem, you can easily write it down. You get basically world lines of fermions and bosons. Remember, fermions cannot cross each other. They are in one dimension. They cannot cross each other. The same thing is true for bosons. Bosons also cannot cross each other because of the hardcore constraint. So the fermions and bosons look almost the same. And so the path integral looks entirely identical except for some boundary effects, right? So world line configurations are self-avoiding walks. So you write down here is a one boson going like that, another boson going like that, or fermions going like this. But then here is another. Here, this boson, this particle has permuted with that particle, right? So here there is no particle permutation. Here particles permute. So this is always positive, whether it's boson or fermion. Whereas here, the physics of bosons and fermions come back and haunt us in the sense that for bosons, this configuration is positive, but for fermions, now the Pauli principle says that there should be a negative weight. In a sense, what has happened is that you started with a configuration, right, a state in your quantum Hilbert space, you went through some change, and then you came back to the same state, but with a negative sign, right? And that's hidden in the quantum mechanical sort of phases as how to evolve this. So in the world line formulation, fermions are a bit tricky because you have to take into account more signs, right? So there was remember we solved the sign problem in some sense of the finite density. In fact, here there are two particles, so in a sense this is sort of the filling, right? So there is a density here. On the other hand, you might say that there is a new problem that is coming because of the fermions, because now I have to take into account the Pauli principle. So fermion world line configurations can create new sign problems due to the Pauli principle. But remember, this is independent of the density. These problems can even exist when there is no density. In some sense, the fermions somehow don't cancel each other in a proper way. There could be a sign problem. So in one-dimensional systems, some of these sign problems are actually often solvable. Especially, for example, if I took an open boundary condition instead of the fermions being in a circle. For example, you could put the fermions in a trap. Then the sign problem is completely solved, right? So then fermions become hardcore bosons. In some cases, you can even change bases, and you can actually show that since the sign problem only comes from the boundaries, you can change bases at the boundaries and solve the sign problem. So one-dimensional problems are much more easier to tackle in that sense. Of course, there are lots of other ideas in one dimension that have become extremely successful in solving one-dimensional problems. So, so if you're doing a one-dimensional problem, if you have a sign problem, maybe there are certain other things to try. Of course, finally, I would like to stress that these one-dimensional problems are excellent toy models for some of the new ideas, right? So, for example, last year, the lattice Thirring model in 1+1 dimension with a chemical potential was considered by this group, and they were sort of trying to explore this Lefschetz-Thimble approach. And actually Paulo Bedak was visiting Duke, he told me that this problem is something that, can you solve the sign problem? And I said, yes, this is a one-dimensional problem, so you can actually solve the sign problem completely. And he was not aware of it. And then he motivated us to do this problem, and now we have sort of a world-line approach to this problem, and we have very precise data, of course, with open boundary conditions. With circular boundary conditions, as I told you, there are sign problems, some of these world-line methods the sign problems are mild because they are coming from the boundary, but they're still there, and one needs to take into account. In fact, the same thing happened more recently, where I became aware of this mass imbalance system of fermions in one dimension, right? They use complex Langevin approach. These authors use complex Langevin approach to solve this problem. Interestingly, in their paper, they never mentioned that the world-line approach has no sign problem in this case. So I think what's true is that some of these well-known ideas are, I think, known to the condensed matter community, but it has not sort of been. And so one-dimensional problems are actually very interesting, simple models, and many of those models can actually be solved very nicely. Of course, we'd like to do higher dimensions, and we have already heard from all the other talks. In fact, Neil Mani introduced how we do QCD nicely yesterday. And so one of the things that we always use in field theories is to use Grassmann variables, right, to talk about fermions. So how is Grassmann variables related to all of these things that I'm talking about, right? The claim I'd like to make is that Grassmann variables basically encode fermion world lines. That's what they do. That's their job, right? Let me explain to you with this very simple example. So let's take a single site. So there's just one site, and there's a fermion there. In fact, I'm going to make a very simple case where h is equal to 0, right? So if I calculate z, I should get 2. And now how does a Grassmann integral do this for us? We write down an action, right? We just write as psi bar dt psi, because there is no Hamiltonian, right? So we write this down, and then we write down the path integral. And now imagine that I take this path integral and remember, it's an exponential of a sum, so I can write it as a product of exponentials, right? And each of these exponential has a psi bar t and psi t plus 1. This is like a hop in time. So I write it as 1 plus psi bar t psi t plus 1. That's all it stops, because they are Grassmann variables. There's no other term. Similarly, so that 1 I leave, and then whenever there is a psi bar t psi t, let's say we draw a line like that. So it's like a directed line. Now there's also a term that looks like e to the minus psi bar t psi t. That's 1 minus that. It stops again. And so let's write it as this object as a loop, because it goes from psi bar t to psi t, right? So there are two terms, if you wish. And now remember, on each side, there should be a Grassmann variable, because otherwise I get a 0 when I do a Grassmann integral. So this object, when I do this calculation at the end of the day, I'm going to get, in terms of these diagrams, a line that just goes straight, where I take this from every side, or I have this from every side. These are the two configurations that will contribute, and so I get a factor of 2. And that's exactly a Grassmann way of writing this object. Right? And that we know in the world line approach, this was the vacuum, this was a fermion world line, or vice versa, depending on how you interpret things. Right? So in a sense, Grassmann variables just encode world line configurations. That's all they do for us. Right? So in a general background, so suppose, for example, the fermions were hopping around in your lattice, and there was a background field sigma, and if I write down what this object is, as I just mentioned, it's a sum of world lines, so let me write it as a sum of world lines there. And that's how one of the configurations will look, let's say. So there will be a psi bar psi, psi bar psi, psi, it's hopping, right? Here it just hopped and came back. Here there are mass terms, right? That's how the thing will look. In fact, to see this, all I have to do is to expand this out, and it has 1 minus that, and then just integrate over Grassmann variables. The point is that this object, the weight of each configuration can be negative, right? Because there's no reason why that weight, along especially with the sigma and maybe other things that go in this matrix, that need not be positive at all. So this weight in general will be negative. So if you want to solve a fermion problem, whether it's finite density or not, right? You just have to integrate over many of these world lines and then hope that some of them turn out to be positive, right? So that's exactly how solutions to fermionic theories emerge. So in QCD, we usually integrate over all possible quark lines in a given gauge field. So the traditional solution is take this, sum over all weights, but that's easy to do. And that's the thing that we learned, that it's a Gaussian integral, we can do it. And so we get a determinant, right? So if M is a good matrix now, and this is where the physics of the sign problem comes in, is that if M is a good matrix, then the determinant of M is positive, right? So then complex eigenvalues of M come in pairs, maybe real eigenvalues come in pairs, and there are properties of M that we use, and that then gives you the positivity. But that's not the only way that we may need to go. For example, remember, we want to do this integral. We know it's a sum of world lines. Why do we have to sum all possible world lines in one go? Is that the only way to do it? Maybe not. And that is what I was trying to explore some years ago in this Fermion Bag approach, which was motivated by a more older idea with my collaborator Uwe Jens-Wiese, where we did not integrate out all the world lines, and then we looked at smaller parts, and then we called the Meron cluster algorithm there, and we did succeed to solve some sign problems there. So here, we not only consider this, because this we know we can do, and maybe if this is negative, what do you do? That's not going to be physical, because there's going to be some integral over some bosonic fields in the background, right? The sigma was just a background object. So there'll be some integration of that also we need to take into account. So maybe we can sort of combine these two into smaller regions and write it as a sum over positive weights. That was sort of the hope, right? In fact, what we are discovering is that the local physics that is causing these sign problems, if you understood the physics better, you will be able to group things, at least in many ways, and then you might get a sum of positive objects. And now these will be more physical objects that live in space-time, and that's why we call it the bag approach. I'll give you some examples of how this emerges, and we'll see. So let me then consider another class of sign problems that we are still struggling to understand, is frustration. So here there are 3 spin-half particles, right? Remember, I had 2 particles on a circle, right? There were charges with a chemical potential. Now there's the third example, is spin-half objects, right? Sort of like fermions if you wish, but they are basically spins or sort of atoms stuck to positions, but they interact with each other because the spin can change. This is a famous example where you have a triangular antiferromagnet, right? I had a factor of J in front, so sorry about that. So now in this case, the ground state is 4-fold degenerate. You can actually work it out. There is you basically have to write it as S1 plus S2 plus S3 whole squared, right? Minus S1 squared minus S2 squared minus S3 squared. And so there's a spin 3-half state, which is 4-fold degenerate, and then there's a spin half. There are 2 spin halves which are 4-fold degenerate. And so if I take this object and try to write the partition function, the naive thing to do would be to expand in the basis, let's say SZ, right? You can choose one of the SZ bases. And this is how people usually do their calculations. And then for every hop, spin hop, you can actually argue, because of the Hamiltonian being positive here, e to the minus of that gives you a negative sign. Right? So every spin hop is negative, but then notice, I can start from here, hop, hop, hop. So there are 3 hops, and you get a negative sign. So that makes this weight, in general, negative. So if you write down the path integral in the usual naive way of spin SZ basis, then you do get a sign problem. Interestingly, such sign problems, at least in a class of models, can actually be solved. Not many people have explored other bases, right? For example, just a couple of years ago, there was a nice paper where they showed that instead of this, if you actually look at hybridization, so take these 2 and write it as spin 1 and spin 0 objects, right? This is a very simple example, but it can actually solve a whole bunch of many body systems which look completely frustrated in the original basis, but then if you write it in this combined basis, you can actually solve the sign problem. So there's a lot of room for creativity, I would say, people have not explored. And in fact, some of these papers actually show that very nicely. So what is the current state of R to solve sign problems? I would say there are two basic approaches. One I call ideas, and another I call solutions. Right? The ideas is that there is not clear proof that the thing is going to work, because either it's mathematically not very clear, maybe there are proofs that will say that it may not work in certain cases, right? And then there are others where things have not yet been shown that it would work. For example, in this case, I call the fixed node approximation, which makes a very, it's lots of applications of this object. It's not completely clear where it fails. In fact, I've asked some of the experts, and they'll say it works, but are there places where it fails? It's not very clear. So I'm a bit skeptical. There's the complex Langevin approach, which is very, very famous in QCD, where it's known that in certain cases it works beautifully, but in certain cases the mathematical proof fails in the sense that there can be runaway solutions. There's this new idea of Lefschetz thimbles, where in principle you're on a completely rigorous mathematical track, but I think the way to solve the sign problem would be that if one of the thimbles sort of dominates in the thermodynamic limit, then maybe the solution is solved. On the other hand, if even two of them contribute, then maybe with different phases you might run into trouble. So that's something, the jury is still out, I would say, whether it will be helpful, but it's much more on a stronger track. So that's something to think about. So in fact, our work, which I just mentioned, was basically to give them clear data based on the worldline approach. See if you can reproduce this data. That would be great, but they have not yet come back. So anyway, the other thing is to just be creative and find a new representation that solves the sign problem exactly. This is, of course, not trivial. Maybe there are some problems where you may not be able to even do this. And so here I would say the worldline approach for many bosonic models and even gauge theories, abelian gauge theories, things have worked beautifully here. The Fermion bags, the Meron cluster, the multi-level algorithms, all of them actually solve the exponential problem and really give you some hope. Now I want to give you a take-home sort of simple example where you can show that there is a non-trivial QFT where it seems like the traditional method is the sign problem is very difficult to solve, but actually the solution exists. And so it perhaps gives you some motivation for creativity. So consider a simple lattice Yukawa model. This is not at finite density, by the way. This is at zero density. And as I mentioned to you, sign problems don't necessarily come from finite density. They can come just because fermions don't cancel each other, right? Fermionic sign problem can always be there. In this case, there is a Yukawa model, so there's a bosonic action which we already encountered in the simple case, right, of the charge. So I'm taking the same theory, just an XY model. It's positive, so there is no sign problem from the bosonic part. And then I write the fermionic action itself, which is basically a massless staggered fermions, right, coupled to a Yukawa-like coupling, right? So every psi bar xix, that's like a mass term, but it's coupled to this field e to the I theta on that particular site. With the sign e to the epsilon x, and that's because of a particular symmetry I'll mention in a minute. So that's staggered fermions, that's epsilon x takes plus or minus charge. It's basically a chiral charge, if you want. And I'm coupling the mass to the chiral charge because this, so now this whole theory is invariant under U1 chiral transformation. So it's a U1 Yukawa model, if you wish. Now, I'm going to focus not on the Yukawa part because that's also solvable, but I'm going to focus on restricting the angle to a Z3 charge. And the reason is because of the following. So there's some recent interest in this particular model, and that's why another way to think about that this model is not just cooked up, it has some interesting physics. So consider, for example, graphene-like model with some kind of a nearest neighbor interaction that can induce what we call a Kekule VBS phase, right? So this is like graphene with some interaction, and there is a quantum critical point that in principle you can go through. In fact, this particular quantum critical point is supposed to be describable by a Z3 Yukawa model. So this is like a Yukawa model we just constructed. So it has been proposed that typically a Z3 model has a first order transition that we all know. I think the QCD community knows quite a bit about the Z3 models because of the, there is no critical fixed point in the Z3 space. So there is a first order transition. However, because of the presence of fermions, the claim is that this transition becomes second order. So it's an interesting twist on the physics of fermions, right? So the phase diagram of the model is pretty interesting. So you have a kappa, which is basically the XY model coupling. And if I decouple the fermions completely, I get a first order transition there. And that's well known, right? Now, if I now add the Yukawa coupling, the claim is that that first order transition will end at a critical endpoint, and then there will be a second order phase transition, and that's what this phase transition is all about. So it will be interesting to study the physics of this particular model if we can in a lattice field theory calculation. Seems like the simplest model one can think of. Now, let's talk about the traditional approach, how I would have done this calculation without this knowledge of all these world lines and all that, Fermion bags and all that. So I would take this model, the partition function is pretty straightforward. I just write down exponential of the bosonic action and then the fermionic part, right? And it's very nice, so it is written in a quadratic form, so I just integrate this out and I get a determinant. Now the determinant of a matrix, the matrix has two parts. One is this part of the matrix, which is anti-symmetric. You can actually see this part of staggered fermions. There is no gauge field or there's nothing. So this is just free fermions, but then it's anti-symmetric. So this is one of those good matrices that you'd like, right? Which has positive determinants. On the other hand, that property is now spoiled by this because there is this Zx, there is this local bosonic term that appears on the diagonal. It's all fluctuating phases, right? You can go back and construct a simple matrix of this type and you will see that the determinant is actually complex. Right? So that matrix has a nice property, but the source of the problem comes from this coupling, and the determinant is complex. At this stage, I wouldn't know what is the difference between this and just at this level, what is the difference between this sign problem and the sign problem in QCD. So it looks equally bad. It has a terrible sign problem, right? Of course, this is not a gauge theory, so the physics is completely different. But in the sense of just sign problems, if we just look at it, you just say there is a bad sign problem, you'll just give up. On the other hand, the sign problem is actually completely solvable. The idea is to consider this particular thing and not integrate over all world lines, which is what you would do, right, in the traditional approach. Let's look at what this term is doing. This term was the thing that was causing the sign problem, so let's say what that term does. So I expand this out as 1 plus that object, right? And whenever I get that object, remember it is one of those mass-like terms, insertions in my world line approach. So this is what I call a monomer field. So I'm going to, for each of these terms, remember it's a exponential of a sum. So it's a product of exponentials. So for each of these terms, I have two terms, either a 1 without a monomer, that's a 0. And if I get this term, that's a monomer. So then I can rewrite this whole object as a sum over a monomer field where I tell you where the zeros and ones exist, right? And then I write this down. So all I'm doing is this term has disappeared now. It now appears in this sum over monomer field. And then wherever the monomers are on 0, I just write this down, right? So that's psi bar psi, the minus psi bar psi, and then the Zx to the power epsilons. So pictorially, I think about sort of in this integral as representing, remember Grassmann integrals are all sum over world lines. There are specific world lines that appear here, right? Since these appear, I cannot have any other world line from these fermions entering that site, right? Because of the Grassmann constraint. So there are specific world lines coming from these objects, which are interaction sites, and then there are, of course, world lines that come from the remaining Grassmann integral. When I do the full path integral, I get sum over all the monomer fields. I get k monomer configuration, so there's a g to the k. I have this object where I've absorbed all the z's into the bosonic part, and then there is this fermionic part, right? Now let's perform the Grassmann integral over the monomer fields first. We just get a 1, right? It's just psi bar psi with a minus sign actually. Just get 1. So all these sites have disappeared. So each monomer site is like a local in my language. So these sites should be dropped when we perform the remaining Grassmann integral. So the full path integral has now 2 parts. One is the fermionic part and one is the bosonic part. In the fermionic part, I have this prime that reminds me that I have to drop all the sites that had monomers in them, right? And so that configuration looks like this. So these are the sites which had monomers. I drop them, and then I do the remaining fermionic integral, but that's just a free fermion hopping around in this remaining place, right? So I can do that, and it's a sum over all world lines. Each world line could have a sign, but then if I integrate over all of that, we'll see in a minute that will be positive. Oh, this is basically the bosonic theory, and now it has these insertions of sources, right? So bosonic sum has these sources, and we'll consider both of these separately in a minute. So the fermionic term is now completely positive, as I just mentioned. I just do a integral over all Grassmann fields, the sum over all world lines, except not on these monomer sites, and I get the determinant of this matrix with these sites thrown away, right? But that's an antisymmetric matrix. It's positive. Determinant is positive or 0. If it's 0, it's fine. I just don't generate them, right? So what about the bosonic theory? The bosonic theory now has a sign problem. Notice that this is no longer positive. The exponential of that was positive because that's a real action, but these insertions create signs. So the sign problem has now shifted into the bosonic theory. However, we know how to solve that. Remember, we said that these sources are just sources of these, it's like introducing chemical potential. We know how to solve them, so you expand this out in terms of world lines of these Z3 spins, right? And so now you introduce a bond variable on each of these sites, on each of these bonds. 0 means there's no Z3 current. Otherwise, there are Z3 currents in the theory. And so I can then write down this object as a sum over bond variables, integer bond variables. Now there are product of these that come from each bond, right? And then the Z itself is just a simple Z power some number, right? And if I sum over all Z3, it's like going to just introduce a constraint. So if you perform a sum over Z variables, I just get a constraint. And so the whole thing is just positive except for the constraint, right? So now I have, for a given monomer field, all the possible world lines. These are called the Z3 world lines. So 3 of them can originate on a site, 3 of them can annihilate on a site. Otherwise, there are these source terms where they can come and go. So except for the Z3 constraint, everything is positive again. So I've been able to rewrite a problem with a sign problem with something which has no sign problem. So I've changed the variables, which helped me to do that. So the partition function now can be written like that, and the sign problem is completely solved. How does it come?
I mean, the problem originally was the determinant, the answer, and it contained a term with a G,
right? Which was
and so you could also, in principle, take the determinant you had at the beginning and then make an expansion. Or
that's what I did.
Essentially, it's the same thing, no?
Yeah,
more or less.
Same thing. Yeah.
Okay.
Yeah, it's just thinking about it slightly differently, but
okay.
Yeah.
Sure.
So that was just a sort of an example for you to take home that sometimes very hard sign problem at least looks hard just because we haven't thought through deeply about it, right? Here now I want to give you another solution. Now I have only 15 minutes. Okay, let's see. 2 solutions where I want to say that sometimes you might be able to solve the sign problem in one way, but then maybe there's another solution that is perhaps more efficient, as I mentioned to you earlier. So here is a sign problem. You found one solution, you found another solution. This solution has an inefficient algorithm. That solution has an efficient algorithm. So that's smart. I'm going to explain to you. So let's take this other model, and this model has played an interesting role over the, let's say, the mid-90s, where 4 fermion field theories were constructed and solved. So the way traditionally this model will be solved is that, again, you have massless staggered fermions coupled to a neighboring psi bar psi on neighboring sites, right? So the free, so this part just describes free massless fermions, and as I mentioned to you, it has a nice property that it's antisymmetric. The traditional solution would be to introduce an auxiliary field to write this as a fermion bilinear. So now I'm introducing a bond variable because it's on a bond, right? But I introduce it in such a way that this is positive and this is negative, and this is something that will be easy to understand. So once I introduce this, what we call the Hubbard-Stratonovich transformation, you can write down the free fermion part, and now a term which is also antisymmetric. Remember, there was an antisymmetric matrix here. Now I add an antisymmetric matrix which is fluctuating. So in fact, this determinant is actually antisymmetric and has no sign problem. So you declare victory, that there is no sign problem, so here is a solution to the problem, and we try to solve it. But imagine, suppose I want to solve this at large coupling. You might say this is not interesting, and we'll think about that later on, but for some reason I want to understand the physics at large coupling. At large coupling, notice that u times the sigma, the fluctuations, are going to dominate. So the fluctuation will be dominant, and it will be like a strong coupling theory, right? It's actually a gauge theory with things living on bonds. So it's a strongly coupled gauge theory, and it's known from QCD calculations that such, if you try to do an HMC in such a background, it will be like terrible because this M is extremely singular, lots of small eigenvalues. So although you have a solution to a sign problem, it leads to a really inefficient algorithm at the end. However, think about this other approach that I tried to introduce in this Yukawa model, but here I take this and write it as 1 minus that, right? So now this is a bond variable, and you can actually show that if you actually write this out, actually this must be a positive sign. I think I missed this sign mistake here. Yeah, so then you write it as 1, if the 1 means there is no bond, and if you put this, there's a bond. So this is like instead of a monomer field, now there will be a dimer field. And so you introduce a dimer field, and then these dimer fields can take either 0 or 1. And then as before, you have these dimer objects, you integrate over Grassmann variables on these dimer objects. So there the fermions are sort of frozen, so there are local fermion bags here. But then there are free fermion bags where the fermions can hop around freely, right? And so in this case, actually, if you do the calculation, you get the determinant of a bag. But at very strong coupling, in fact, the bags break up because there are lots of monomers which sort of break up the whole space-time into small bags. And so the matrix becomes extremely small, and you really get a very efficient algorithm at large U. So you have another solution which is better. So you have to look for such solutions, only then you learn how to solve the problem efficiently. Now here there is another a twist to this whole thing. Instead of integrating over these Grassmann variables and writing them as dimers, you can think about doing this calculation just using Wick contractions, right? So it's a free theory, and I can write down the Wick's theorem there and write down all possible diagrams. If you actually do sum over all possible Feynman diagrams in this case, you actually get a determinant of all possible propagators here, right? So this is just a dual way of thinking about it. I'm thinking about it in terms of the weak coupling expansion. And so you actually, for very small couplings, this approach is much better, and you get actually small matrices, and again, things become very efficient. So there is some kind of a duality between weak and strong coupling, even in the algorithmic sense. And this maybe goes back to this question that I raised yesterday about this theory of resurgence and things like that. So things you can write down and, in fact, calculate, in some sense, the coefficients of the perturbative expansion, both at weak coupling and strong coupling, very accurately in these kind of models. And so it might be interesting to sort of learn if there are certain dualities that go beyond this. And in fact, I can actually see that there is a connection between this and that, because there is the determinant, whoops. This is exactly the same as this. So this determinant of the bag is the same as the determinant of the propagator. So there's a duality in that sense. I have 10 more minutes. We'll see if I can finish this. So I have only a few more slides. So next I want to talk a bit about how issues of signal to noise ratio affects calculation. So for example, this was something that we did recently. So we considered the XY model, right, on the lattice in 3 dimensions. If I tune the coupling to a specific value, the theory describes the Wilson-Fisher fixed point at the infrared. And this is something that we heard in the last class, last lecture, that we can think about conformal field theories and understand their properties. So here, our approach was to figure out what properties does this conformal fixed point have, but at very large charges. So what do I mean by that? So suppose I want to compute this correlation function, which is e to the iq theta time and e to the minus iq theta actually at y. So there's a typo here. So I put very large charge source and sink insertions, right, and pull them apart. And at the conformal point, I want to know how the conformal dimensions go. So this d of q is a conformal dimension for this theory. So there were predictions. In fact, one of our collaborators and his collaborators had a prediction a couple of years ago that this d of q should have this particular form. We can actually understand the leading form pretty easily through a semi-classical analysis. And they showed that you can actually do some kind of an effective theory starting from a conformal theory, but because of the presence of the charge, you're introducing some kind of a scale in the problem, and that then allows you to do some kind of an EFT approach to this whole problem. And they predicted that this d of q will have a series expansion where all these coefficients will be universal, right? So can you find these coefficients? But remember, to find these coefficients, we need to compute d of q at large values of q. So the challenge was to extract these coefficients in this expansion, and so can we calculate the c of q for large values of q when x and y are very far away? Now, since d of q grows with q to the 3/2, so this thing falls quite rapidly, right? Notice I'm going to average things of the order of 1. They're just phases, right? To calculate a very tiny quantity here. Well, that's your signal to noise ratio problem, right? And so this is why I don't think anybody could do this before. So that large Q, it is very difficult to compute these correlation functions, and the Monte Carlo suffers from signal to noise ratio problems. But interestingly, in this world line approach, and using some of these worm algorithms, we can actually solve this problem completely. So what we did was we calculated the ratio of 2 different charges, Q and Q minus 1, both at very large Q, and here are the kind of results that we could get. We could get it extremely accurately. Notice how small numbers that we needed to calculate. So if we add 1s and minus 1s to get this kind of small number, it would be almost impossible, right, with statistics. But we can actually do this with these worm algorithm ideas. And so then we actually computed this d of q, and our predictions show these numbers. But interestingly, notice that although this fits beautifully for these large values of q, if I just take these 3 coefficients, even delta q of 1 is almost accurately determined. So we believe that this may be a nice way to think about an alternative way, like the epsilon expansion. Maybe there is a large q expansion that can actually be done to compute critical exponents. So that's one of our things. So finally, I just wanted to leave you with just some thoughts on Hamiltonian lattice field theories. I will talk more about it in my research talk later on. So the question is, can we construct and study strongly interacting massless Dirac fermions, theories of strongly interacting massless Dirac fermions in the Hamiltonian formulation? Now, of course, this has been done because of the interest in graphene by many, many people, right? These days, there's a lot of work in condensed matter community. The question, I guess, is the Hamiltonian approach, even with staggered fermions, we know all these beautiful properties of staggered fermions. So if I go to the Hamiltonian approach, is there something that we can learn? Clearly, there is less fermion doubling, right? And there are more symmetries, so maybe we can learn more. And interestingly, there is a whole new set of models that we can actually solve now because of some recent discoveries of new solutions to sign problems. So this all got motivated when my student discovered an interesting formula some years ago, and then that was followed by more work by some Chinese group. The idea is, for example, if you considered a simple Hamiltonian of this type where there is no spin, just simple a spinless fermion hopping on a lattice with some kind of nearest neighbor interaction, this model is such that there is a particle-hole symmetry. Traditionally, if you try to approach this in the usual way, especially if you wanted to write a lattice field theory approach, you would perhaps come up with these coherent states and introduce Grassmann variables of this type. But that approach breaks particle-hole symmetry, and this is something we can actually show. This is what we showed. And then the question is, can you keep the particle-hole symmetry and use that? And the trick is to introduce Majorana fermions and not work with C daggers and Cs, and then to construct the partition function, and then the problem is solved. Okay, so with that, I wanted to conclude. So I hope I've convinced you that the solution to sign problems are quite an exciting area of research. They've not been appreciated as such, but they bring together ideas from mathematical physics and some ideas of computational physics, because we want to think about positivity as an important way to think about Monte Carlo methods and things like that. So if you can really reformulate your path integrals in that way, there is a lot of gain, right? So, so usually, I also hopefully introduced to you that sign problems have a physical origin. There's some physics of either a Berry phase or some kind of a different or the right basis states to consider. And then once you think in that new language, then the sign problems are solved. At least that happens in simple cases. The question is, can you then use that insight in a more many-body sense? So that understanding actually was the reason why we could solve some of these other sign problems that I explained to you. Of course, lots of complementary ideas that are being explored. And I want to leave with maybe a biased opinion that I believe that non-trivial solutions, which I gave you one example, may actually emerge if you think more carefully about how physics how physics affects local regions of space-time and how sign problems emerge from local regions of space-time, very similar to the RG type of blocking. So if we think in that language, maybe there are other sign problems that we can solve. Thank you. Whoa.
Any questions?
In the Hamiltonian formalism, if one naively does it by diagonalizing the Hamiltonian, it's the most easiest because that doesn't have any sign problem. But are there ideas like if the Hamiltonian can be block diagonalized, or there are some ways to compute the Hamiltonian efficiently? Or
so there are once you get into the field, there are all kinds of tricks that people know how to do. So for example, the notion of bipartiteness is very helpful in the sense that if you can really put all your degrees of freedom into groups and show that there is no frustration in all of these groups, but then these groups have some kind of a bipartiteness, there is A and B, right? And then you can actually solve certain sign problems more easily, right? So there are all these tricks that you begin to learn. But at the end of the day, I think every problem is in some sense different. So you have to think, give me a problem and then I'll have to think. And it's not like a one solution fits all. That doesn't seem to work, at least in this approach. But this whole concept of exact diagonalization can only be done in small lattices, right? So you can learn quite a bit on the small lattice, but if you want to go slightly bigger, then you're just lost, right? But just mention, maybe there are ways of thinking about exact diagonalizations of small space-time regions, right? And then, as I was mentioning to you, is there some nice way to construct and put all these things together. So this reminds me of some kind of a tensor network kind of idea, but nothing concrete has come out of it, but something to think more about.
So you mentioned very much the bag approach as a solution to the sign problem, but all these cases you discussed are essentially without gauge fields. So is there an example where bag approach can also solve a sign problem with gauge fields?
So yeah, you're right that I didn't mention gauge fields because there were, as I told you, there were two steps I was thinking about. One is solving the sign problem. The next step is to solve it efficiently, right? So typically when it involves gauge fields, as you know very well, gauge fields bring a whole new can of worms when you think about efficiencies. So yeah, that's why there are sign problems that are maybe solvable using the fermion bags and gauge fields, but the second step would be hard. So that's why I don't quite get into that at the moment. But you're right. I think that's one of the ways to think beyond.